Example 1, lesson 2, orbits. Example 1 says this: draw a force diagram for the mass little m in orbit. How about we'll make it the moon, and here's the Earth. What are the forces acting on it? Is there the obvious one? Is gravity acting on the moon? Yeah. Which way, in this case, in this picture? Toward the... so I have this. Oh, still in my highlighter mode. Let's change that. What direction is this force? And what path are we tracing out? A circle. That sounds vaguely familiar to me. Yeah, this is the key idea. When you're moving in an orbit, it's really a circle with gravity pulling you in a circle. So example 2, a 10,000 kilogram satellite is orbiting 20,000 kilometers above. Do me a favor, underline kilometers and underline above. Those are going to be two important words. The Earth's surface. A says, write force equations. You're going to underline a third word, and the third trigger word is orbiting or orbit. As soon as a question tells me that we are in a stable orbit, I can say this. What are the forces acting on this little m? Get the obvious one. Get the obvious one. For part A, you want the equation? It's this. Gravity is what's pulling me in a circle. That's the equation for every circular orbit that we'll be looking at. We start out there, and then we'll derive whatever we need to Samira from there. What does B want me to find, Samira? Oh, so you know what? I'm pretty sure I'm going to use the mv squared over r. The other thing they could have asked for is the orbital period, how long it takes the moon or the satellite. This is the satellite this time. How long it takes the satellite to go around the Earth. And then I would use the m 4 pi squared r over t squared. Now, I cannot, don't write this down, I can't use that because this far out, I don't think little g is 9.8. I have to use the universal equation for gravity. Big G, big M, little m over r squared. Oh. What do you notice? Or do you notice anything at all? What cancels? It turns out once you're in orbit, it doesn't matter how big your mass is. Everything that has this orbital speed will orbit at that speed regardless of their mass. Everything at this radius will orbit at the same speed. Okay? So that's kind of handy. And then there's one more thing. If I multiplied this r on the right to the top over here, I'd have an r on the top and an r squared on the bottom. One of the r's cancels. Here's how I show it. I cross out the squared and I cross out that r. Now this is going to be a bit tricky because Victor, in another set of equations, r's won't cancel, and kids get a little cancel happy with the r's, and so be very careful that you think it through carefully, that, oh, I could multiply the right-hand r to the top on the left, and it would cancel with one of the r squareds on the bottom. What are we trying to find? How did I get the v by itself? Except it's not all by itself. Yeah. Turns out, if you want orbital speed, it's the square root of big G, big M over R. I've never bothered memorizing it because to me it's a one-line derivation. If you wanted to add it to your blue sheet, I guess you could, but I just derive it. I got limited room in my brain as I'm getting older, and so I just know gravity is what's pulling me in a circle. And how do I know that? My trigger word is the word orbit. Now, there are non-circular orbits. There are elliptical orbits as well. Those are orbits that are shaped kind of like that. We don't have the math to deal with those, although those of you that are in calculus, I think you might have looked at the ellipse at the very, very beginning of the year, and there's some lovely stuff you can do there as well. Our planets are in elliptical orbits around the sun, not circular, although the orbits that the planets are doing are so nearly circular that when you look at them with the naked eye, they look like circles. You may have seen textbooks that show you pictures of the solar system and they show the planetary orbits like that. They're not. We actually graphed, I think we graphed the orbit of the Earth by hand on using software, and when it graphed it, you couldn't tell from the naked eye that it wasn't a circle. There's no, unless you had told me it was an ellipse and told me to go hunting for it, I wouldn't have guessed it was an ellipse. Anyways, that's a long rant to say, Maddie, we're stuck with circles right now. This R is orbital radius. It's from the center to the edge. That's R. Is it 20,000? Nina, why not? Okay, so the first thing I'm going to do is I'm going to multiply that 20,000 by what? Okay, and you know what? I'm going to be lazy. You can do it on your calculator if you need to, but it has 4 zeros. When I multiply by 1,000, there's going to be 3 extra zeros. I'm going to cross out the 20,000, and I'm going to write it as 2 times 10 to the 7th. So is R 2 times 10 to the 7th? No. Why not? What's the next word that we underlined? The word right next to kilometers, the next word, huh? This right here is an altitude, and that's 2 times 10 to the 7th. I need to convert that to a radius measured from the center of the Earth. How will I do that? Okay, so in our notes, now, if you did this intuitively using your calculator in your homework, Johnny, I won't freak out, but in our notes, then let's make a little note here. Our orb is altitude plus our Earth, so that when we're studying later or whatever, you know how the heck we got that. Sometimes the question will give you the orbital radius measured from the center. Often, if I'm being nice when I'm making up a question, and I think the rest of the question has enough curveballs, I'll just give you the orbital radius. In rocket science, though, typically what you'll know is the altitude, and you'll have to add in the radius of the Earth. So the orbital radius is going to be 2 times 10 to the 7th plus, it's 6 point something, but I can't remember the rest of it. It's on your sheet. That's why I said get your formula sheet out. 6.38 times 10 to the, okay. So it's going to be 2 scientific notation 7 plus 6.38 scientific notation 6. So I get our orb, and I'm not going to round this off because I'm going to be using this, 2.638 times 10 to the 7th. Alrighty, here we go. So V orb, and this is just going to take up space because the numbers are big and yucky. It's the universe we live in. It's going to be big square root G. What was big G? This was our universal gravitational constant that Cavendish discovered. And I'm pausing. Please make sure you know where that is on your sheet. Yes? 6.67 times 10 to the negative 11. M it's the mass of the planet. In this case, it's the Earth. We'll also do other planets, but if I do that, I'll almost always give you the mass of the planet in the question. The 3 you have are the mass of the moon, the mass of the sun, and the mass of the Earth on your sheet. 5 point something times 10 to the 24th, all divided by 2.638 times 10 to the 7th. What's our orbital speed? All of you need to practice typing these in because we're going to be getting into some pretty heavy-duty, ugly calculations. And so you want to figure out how your calculator does this. On mine, it's going to be 6.67 times 10 to the negative 11 times 5.98, scientific notation button 24, divided by, I can go answer button because I have that stored there, and then I go square root answer button. Usually orbital speeds are in the thousands of meters per second. Unless you're really far from the Earth, then you might be in the hundreds of meters per second, but you got to be pretty far away from Earth's gravitational field to stay in orbit going that slowly. 3888, so how about 3.89 times 10 to the third? Got that okay, Johnny? Or oh, okay, because your eyes got really big as though you hadn't seen that number before. 3.89 times 10 to the third meters per second. So just shy of 4 kilometers a second. Is this satellite moving? Be obvious. Slowly or quickly? Does this satellite have kinetic energy? Is it moving? So does it have kinetic energy? Where'd that energy come from? A big chunk of the rocket fuel that we're sending up to launch things into orbit is the rocket fuel required to get them going to the right speed. We have to use some fuel to get them to the altitude because there's a change in potential energy as well. But a lot of the rocket fuel is, once you're up there, we got to get you moving. So note that orbital speed doesn't depend on the mass of the orbiting object, the little m canceled. It only depends on orbital radius and central mass. I'll write this as an equation, V orb equals the square root of big G, big M over R orb. But I really derived it by saying gravity is what's pulling me in a circle, because that part I can remember. You have young brains. I always have a few students that happen to just memorize this one. And if you pull it out on a test or a quiz and you've memorized it correctly, James, I won't make you walk through this derivation, but you'll notice in my answer keys, I give marks for doing this if you haven't memorized it, right? Next page over. It says this, fill in the proof below to show that when an object is in orbit, let me just pause for 1 second. It's okay. Okay. We want to prove that objects are in free fall. Let's see. First of all, what path is this object tracing out? Sorry? What path is this object tracing out? A circle. So we do have an inwards acceleration. So we know that its acceleration is going to be v squared over r. But on the previous page, we got an expression for orbital speed. It was the square root of big G, big M over R. So if I had an expression for V squared, I think all that would happen is the square root would vanish. In other words, I think V equals big G, big M over R if I substitute V squared. Is that okay? And so we get this. A equals big G, big M over R, and there was already an R down there from the V squared over R. But what's a better way to write RR? Okay, I end up with big G, big M over R squared. Compare that to gravitational field strength, and you'll realize they're the same, that little a equals little g, universal g. And so what that means is all orbiting objects are in free fall. Now, I taught my students that in Physics 11 last year. We explained that the reason astronauts float on the International Space Station is not because there's no gravity, it's because there's no normal force. And we said, when do you experience no normal force? When would a scale read 0 if you were standing on it? When you're in free fall. So hopefully that isn't new to you. But the real question then is, why don't we come crashing into the ground? So in an ingenious analysis of orbits, Newton imagined standing on top of a large mountain and firing a cannonball horizontally. And so he said, if you put in a certain amount of gunpowder, it would land right there. If you put in more gunpowder, it would land right there. If you put in more gunpowder, it would land right there. If you put in more gunpowder, it would land right there. And he said, it seems to me that there is just the right amount of gunpowder that I could put in so that it would just keep going around and around and around and around. It would fall, but it would never get closer to the Earth. We would give it just the right kinetic energy, sideways speed, centripetal speed, so that even though it was technically falling, it just always missed the Earth. That's what an orbit is. So it means that in orbits things in orbit are always falling towards the Earth, even if they never get there. This explains why astronauts seem to float around on the space shuttle or on the International Space Station. Both passengers and the ship and the station are in free fall, all falling at the same rate. Therefore, the ship can't exert a normal force, and they experience apparent weightlessness. Apparent weightlessness is when the normal force is zero. True weightlessness is when gravity is zero, and that's if you move away from any planets out to the very, very edge of the universe, and you're not in any gravitational fields anywhere, then you'll truly be weightless, because there's no gravity. Usually we're talking about apparent weightlessness. And it also means that astronauts experience continuously, until they get used to it, the physiological feeling of falling. They get sick the first couple of days. You're throwing up a lot. And then you get used to it, and then you feel like I think Chris Hadfield said, the nice thing about being on the space station for all the time that he was, you become a space native. He said, it becomes second nature to fly everywhere. Put your pencil down, look up. So what can we do with this? There's going to be some orbit questions in your future, and they're pretty cool. When we're talking about orbits, there are four things: orbital radius, orbital speed, orbital period, and altitude. If I give you any one of them, you can find the other three. That's what our argument is going to be. In a cartoon, a character kicks a football the wrong way, but the football orbits the Earth and still goes through the uprights from the other side. What speed was the football moving? First of all, underline the word orbits. That's our trigger word. Thomas, what's A asking me to find?
The speed of the football.
What path are we tracing out?
Circle.
What force is pulling us in a circle?
FC.
What force is pulling us in a circle?
Gravity.
So we're going to start out by saying, as soon as I see the word orbits, gravity is what's pulling me in a circle. Now, there will be situations later on where we're not in orbit, where we're just up there, we're going to come crashing back down. We can't say gravity is pulling us in a circle. I can't use mg for gravity. Why not? Because we're way out there. So we're going to use big G, big M, little m over r squared equals m. And then, don't write this down, I'm going to think AC. Thomas, am I going to use the one with the V or the one with the period in it? What's A asking me to find? I'm going to use the V squared over R. Again, a little m cancels and one of the r's cancels. And I get the same expression we had before. V orb equals the square root of big G, big M over R orb, where big M is the planet that's pulling us around in a circle. Okay, so I'm going to get, have I got lots of room? Yeah, I did give you lots of room. Okay, so I'm going to get V orb equals the square root of 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, 6.38 times 10 to the 6th. Is that the radius of the Earth, I think? Going from memory here. Yeah? Again, I'm hoping all of you have clued in where these are on your sheet. If you wanted to orbit right at the Earth's surface, how fast would you need to be traveling? I got 7906, sorry, 7907 if I round off properly. I'll go 7,910 meters per second. Okay. Jacqueline, what does B want me to find? Period, I think. What path are we tracing out? What's pulling us in a circle? Gravity is what's pulling me in a circle. I'm still going to go big G, big M, little m over r squared, but now I'm not going to use mv squared over r. I'm going to use m 4 pi squared r over t squared. Oh, I noticed something. Jacqueline, what do you notice? Okay, so here as well, it doesn't matter how big your satellite is, it's going to have the same period and the same speed. Does an r cancel this time? This is the one where often kids make a sloppy mistake. Yeah, no r's cancel, because either I'd multiply the r squared up to here and get an r cubed, or I'd multiply this r down to there and get an r cubed. But the most common mistake is I see kids do this, and unfortunately now you just ended into ugliness. And if this is multiple choice, I guarantee I'll have one answer where you've done that. Sorry, but I will. What are we trying to find, Jacqueline? Where is the t right now? On the... Bleh. Oh, wait. Let's multiply the t up to the top there. Let's multiply the r squared up to the top there. And let's move the big G, big M to the bottom. The shortcut, Johnny, is when you have one fraction equals one fraction, stuff moves diagonally. So I end up with this. T squared equals 4 pi squared r cubed all over big G, big M. Of course, Jacqueline, let's get to t squared by itself. Oh. It was this unit that I had in mind way back in Physics 11 when I started nudging you to do formula manipulation, because I think it makes this unit, Victor, way easier. Now it's plug and chug, complicated plug and chug, and I want to insist all of you try this on your calculator. But let's plug in the numbers first of all. We're going to get square root of 4 pi squared 6.38 times 10 to the 6th cubed all over 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th. Need to make sure you can remember how to cube things. 4 pi squared 6.38 times 10 to the 6th all to the 3rd power. On mine, I know I don't need brackets if I use scientific notation. You'll have to play around with your calculator and see how your operating system works. Divided by bracket 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th. That's way too big. Square root of that. And you should get 5,070 seconds. Yes? No? By the way, just to put that in context, if I divide by 60, you're going around the Earth every 84.5 minutes. International Space Station goes around the Earth every roughly 96 minutes, give or take. Which is, that's fast. Pretty fast. Michael, can you read C to me? Could you read a little louder? So why is this impossible, but it would be possible on the moon? What's the big issue here? Why can't you orbit around the Earth, let's say right at the Earth's surface? Or even, let's say, a couple hundred meters up so you're avoiding buildings. Why would this still be an issue? That sounded like a phone that went off in my classroom. First of all, we got to pause. What was that? Yeah, air resistance. Air resistance is the big issue. On the moon, no air resistance. This would be very doable. In fact, if we do ever have a moon base, probably a very easy way to set up satellites and orbits and such would be, what's the highest mountain on the moon? Set everything maybe 100 meters higher than that. Easy peasy. Example 5. I like example 5. I like example 5. I like example 5. Suppose we want a weather satellite to orbit, you know what? Everybody underline the word orbit. The Earth every 300 minutes. Maddie, what does A want me to find? Did you say orbit? Gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals m. Am I going to use the circular acceleration with the v in it, or am I going to use the circular acceleration with the t in it? How do you know? Except, you know what? I'm going to go minutes. How would I change 300 minutes to seconds? And double check me, it's 18,000, yes? And I think I've told you often, if you give me yucky units in the actual question, I'll cross out the wrong information and just rewrite it, so there's no way I'll accidentally use that 300. So I'm going to use the m4 pi squared r over t squared. And yeah, it turns out they didn't need to tell me the mass of the satellite. Where won't the mass cancel? Later on, when we try and calculate how much rocket fuel you need to put stuff in orbit, there the little m won't cancel because it takes way more rocket fuel to put a bigger object in orbit. But to keep it up there, easy peasy. What am I trying to find here, Maddie? Let's get the r by itself. I think I'm going to multiply that up to there, and I'll end up, can you see, with an r cubed? I'm going to multiply the t squared up to there. I'll end up with equal sign and a big G, a big M, and a t squared. And then what will I do with that 4 pi squared? Sorry? Divide it. It's going to end up over here. And there's a reason I like this question. How do you get rid of a cubed? Holy smokes, you mean cube root is actually useful? It's not just something they teach us in math to annoy us? And so, my children, cross out the cubed cube root. You're going to need to figure out right now today where your cube root button is on your calculator. And if you can't find it, I'll help you with it in just a second, but let me write this out first. R equals the cube root of 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, 18,000, don't forget the squared, Mr. Dueck, all divided by 4 pi squared. So, I'll pause the video. Let's quickly type this in, Mr. Dueck. Clear. 6.67 scientific notation button, negative 11 times 5.98 scientific notation button, 24 times 18,000 squared divided by bracket 4 pi squared. Do a quick typo check. That looks good to me. For me, cube root is math, option number 4, cube root answer button. You get 1484809.9. I'm going to write this in scientific notation. How about 1.48 times 10 to the 1, 2, 3, 4, 5, 6, 7? Yes? If you wanted that in kilometers, divide by 1,000. William, no? Or Johnny, no? Can't find where cube root is? Okay. Victor, what's B you want me to find? Isn't that what we just found? In fact, here's what we found. This is orbital radius. And what we would like to find is that distance right there. How could I figure out the altitude? Take the orbital radius and do what? Subtract what? Radius of whatever planet we're talking about, in this case, radius of the Earth. So altitude is going to be R orb minus R Earth. Altitude is going to be, and I have this sitting here, minus, is it 6.38 times 10 to the 6th? Yes? And so I get an altitude of 1, 2, 3, 4, 5, 6, 8.47 times 10 to the 6 meters. Or if they want it in kilometers, this satellite is orbiting at 8,500 roughly kilometers from above the surface of the Earth. Is that high, Mr. Dueck? Yeah. Yeah. 300 minutes. Remember, the International Space Station was only 96 minutes to go around the Earth. International Space Station orbits at about 300 kilometers above the Earth's surface. So this will be significantly further than the International Space Station by a long shot. C. What's the satellite's orbital velocity? I got a couple of options here. Draw a little line down the middle of the page. First of all, did they say orbit? I could go gravity is what's pulling me in a circle, and I could end up with V orb equals the square root of big G, big M over R. And that's perfectly acceptable. You would use your answer from part A to get this. The other thing you could have done is you could have said this: circular acceleration equals circular acceleration. You could have said 4 pi squared r over t squared equals v squared over r. And get the v by itself. No matter what, you're going to use your radius that you had to calculate from part A. And I think this left-hand method is a bit cleaner, so I tend to go with this. But every year I have a couple of kids that choose to use this one, and okay, it'll get you there as well. I'm going to go with this one. It's going to be the square root of 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, all over. I could use 1.48 times 10 to the 7th. I'm going to use as much of this as I can since I happen to have it on my screen. I'm going to use 148,48096. 148,48096. I'd like to carry extra sig figs, and that way I haven't introduced a lot of error. If you notice you're off on your third or fourth sig fig compared to what I got, it's probably I was using my answer button whenever possible, and you might not have. Or I was able to do, because I got a multi-line display, even though I didn't use my answer button, I was able to go back and just copy out my answer again. What'd you get? Oh, by the way, I should change that to orbital speed, because velocity should have a direction, tangent to the radius, I guess. But 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th divided by 148,48096. Square root of that. And I've told you, what was the, if we wanted to orbit right on the Earth's surface, what was it, like 8,000 kilometers per second, roughly? As you go further out, you can go slower and slower and slower. So this seems ballpark right to me. 5,180 meters per second. If you want to, then you could say this. R orb was equal to the cube root of, what was it? Big G, big M, T squared, all over 4 pi squared. Can you double check? Did I copy that out right? Yeah? Have I bothered memorizing that? No, gravity is what's pulling me in a circle. That's my fallback. Again, you can add this to your blue sheet if you really feel you want to. I would encourage you not to and just realize, James, gravity is what's pulling me in a circle. What's your homework? Oh, no. Okay, I got another one here, but I got cool videos to show you as well. Pause for a second, put your pencils down. Example 6, I like example 6, I like example 6. Example 6 is a nice question. I've said to you that there are 4 things: orbital speed, orbital radius, orbital period, and altitude. If I give you one, you can find the other 3. So now I'm going to give you a little altitude. Some even give me altitude all year. Nothing? Okay. A satellite has an orbital altitude of 1 point. First of all, orbital. Gravity is what's pulling me in a circle. Of 1.2 times 10 to the 6 meters above the Earth. What's its orbital radius? Not on your sheet. What we're talking about here, Colby, is I've given you this number right here. Let's change colors, Mr. Dueck. Draw the Earth in blue because that works. I've given you this number right here, and you want orbital radius. How do I get the radius? I'll take the altitude, and I'll add radius of the Earth. Yes? Which is what? Sorry? Round it off at all, or is that everything? Because I'm going to be using this, so I would not want to round off. I'd carry as many sig figs as I could. All right. Now we're in familiar territory. William, what does B want me to find? Should say orbital speed. I keep forgetting to change it. I'm going to try and remember to change it today. Did you say orbit? Gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals m. You said speed, v squared over r. One of the r's cancels. The little m cancels. By the way, do you see why last unit I got so mad at people when they forgot to put the m in front of the a because it looks like an expression? When you get to here, the m won't cancel and you'll end up with answers that are way, way off. Or you'll freak out because in this case, I didn't give you the mass. I will often give you the satellite mass just to tempt you not to cancel them. Sorry. And we get v orb equals the square root of big G, big M over R orb. .67 times 10 to the negative 11. 5.98 times 10 to the 24th. All divided by, what was it, 7.58 times 10 to the 6th? Little tricks of the trade. How many of you are able to bring back previous lines, like 5 or 6 previous lines, not just one line back? So, Johnny, what I often do is I start going back. You know what? There's G. There's the mass of the Earth. I know I typed this a few minutes ago. All I need to change is this number here. And yes, I'm that lazy. I'll often do that as well as a little trick of the trade. 7.58 times 10 to the 6th. And square root of that. It's less typing. You get 7250? 7250? Mateo, what's C want me to find? Orbital period? Did you say orbit? Gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals m for pi squared r over t squared. Does an r cancel this time, Mateo? But an m does. This time we want to get t by itself. I'm going to multiply the t squared up to there. And I'm going to have a 4, a pi squared, and r cubed. And then I think divided by big G, big M, square root. For pi squared times r, what was r? 7.58 times 10 to the 6th cubed divided by 6.67. And this is the unit you'll end up doing the most pure calculator typing on. There's just no workaround. The numbers are yucky. Square root of that. Do you get 65, 65? How about 65, 70? Yeah. Seconds. And I don't think there was a part D. No. So this would be a lovely written question on your test. In fact, almost certainly I'll give you one of those 4 things and ask you to find 2 of the other 3 remaining, probably. What's your homework? Number 1 we've talked about. Number 2, I'm giving you the radius of Mercury's orbit. Find Mercury's orbital speed. You didn't give us Mercury's mass. I bet you it cancels. But I did give you the sun's mass. It's on your sheet. You can try number 3. Five is good. I skipped 4. 6 is good. 7 is good. Number 7 says a geosynchronous orbit is one where the satellite stays above the same point at all times. What would the period of a geosynchronous orbit be? 24 hours times 60 minutes times 60 seconds. And so you can calculate the radius of a geosynchronous orbit. Geosynchronous orbits are really useful, but they're all at the same radius and it's getting crowded up there. 9 is good. I skipped 8. 10 is tricky. 12, 13, 14, 15.